Hello everyone. We are going to be looking at properties of determinants. Remember, when we talk of determinants, we are always going to be looking at square matrices. So this theorem says, if you have a square matrix A, then the following four are very important for us. These are the characteristics which prop up for a determinant. The first one is, if you're multiplying one row or a column of A is added to another row or column to produce another matrix B, then the determinants are basically the same of the original matrix and the new matrix you get. If two rows of A are interchanged to produce another matrix B, then this determinant of the new matrix B is negative times determinant of the original matrix A. If one row of A is multiplied by K to produce the new matrix B, then determinant of this new matrix B is K times determinant A. Much more better to have it here than here. Now, if you have a matrix A which has either a row or column of zeros, then determinant of A is already going to be 0. Remember, when we talk about determinants, we are finding by using cofactor expansion. So if you have a row of columns, suppose we have this matrix 1, 0, 0, 0, 3, 0, 0, 0, 0. Say this is 9. What happens? This is a column of zeros. So if I want to find the determinant of this matrix, then I can use this as my column. The moment I use this as my column, I will always get determinant to be 0. So it's very easy when you start looking at matrices given to you. Is there a possibility of having a row or a column to be 0? Awesome. Then that determinant automatically becomes 0. Now, what we're going to do is we're going to apply some of these properties in finding the determinant and making life simpler for us. Let's look at this example. We have a matrix which is a 3 by 3. And now there are many ways we can apply the, find the determinant using cofactor expansion. But if we can apply properties, then we can quickly get answers. Now the best one, if you guys remember, is that if we have a triangular matrix, so in other words, if I can write this matrix in this form, like something here, a non-zero element. Remember, by square, we are having a non-zero. We don't care what these elements are. A non-zero, some element here, anything here. So basically, if I'm having it in an echelon form, so here, I can have a star also. It doesn't matter here. Any element here, any element here. So basically, an echelon form. It doesn't matter anything because determinant of a triangular matrix, remember, is nothing but the multiplication of the diagonal elements. So even the diagonal elements can be 0. Remember, determinant of a matrix is a number. So the idea is if I could write this matrix in an echelon form. So basically getting 0, 0, 0 here. And as I'm doing this, I'm making sure I'm keeping those properties, just which we talked about, in mind when we do them. So when we do this one, if we can write this matrix in an echelon form, then it becomes easy to find the determinant of this because we'll just multiply the elements in the diagonal sequence. Okay, so that's the strategy to do it. So when I have this matrix, now remember what this first theorem was saying of the previous slide, that if you multiply a matrix by a number, a non-zero definitely, and add it to another row, the determinant will always remain the same. So what I'm doing is I'm trying to, if I'm making an echelon form, I would try to get this 0 and this 0. And this 0, okay? So the first thing we can do is if I multiply the first row by 2 and add it to the second row, the change is in this row. So I get a new matrix, remember equivalent matrices? Guys, we're going back to section 1.1 and 2, every time we go back over there. So what happens when we do this operation? This is a new matrix we get. This will have the same determinant as this one, but our lives become simpler. Remember, this basically is a multiple of these two. So this will be a non-zero element. Oh, great. So we got this one here. Now we have to make this 0. So basically, you're going to add the first and the second, the third and the first row, and changes will be seen in this node. So that's where our new matrix is. So basically we're applying that little, the row reduction algorithm, remember. Now, clearly, we have got a bunch of zeros. Now, this is great, but the thing is, if we could get this row in the third column, and that way we automatically will have a echelon form. But the key point over here is this, guys. When I changed till this point, when I'm doing these two operations, my determinant will not change. It will remain the same. But in order to make our life simpler, I will have to just basically basically swap these, not flip, but say swap is the right word I say. Swap these two rows. Now, when you're swapping the rows, determinant property becomes very evident. And this is the property we have to be careful. If I'm interchanging any two rows, the new determinant will be the negative of the original. So that's what we will be working on. So when we interchange this, we will have a negative in the front of the determinant, and we will get an echelon form. So let's go to the next slide, and we see that happening. Now remember, this was what we had got from the previous slide. So I'm going to interchange these two. When I interchange, I get a negative here, and I get my awesome, great looking echelon form of a matrix inside. And so if I'm looking at the determinant, so I will just simply go and multiply the diagonal elements. These elements, guys, I will multiply. And what is my answer? Negative 15. So basically, when we apply these properties, our calculations become very, very simple. Okay. Now let's look at another example, but here I will try to use a different approach to show that it's not that we always have to apply row operations. We can actually also use some column operations. That's one of the beauty of using properties of determinant. Now, if I'm given this matrix, there are many options to find the determinant. First option is expansion. The cofactor expansion, sorry. Second is, make a, an echelon form, echelon form. Third option is apply some, other properties. So echelon form is literally operating on rows. So I want to show you something different here. I want to say, I can apply columns. I will still get the same answer. So what we're going to do is, then look at this one. I am going to multiply this row 2 times and add it to this. Notice 4, 6, and 9. So multiple of 2. Multiple of 2, so this one is multiple of 2. This is not multiple, but these two can easily get cancelled. So the idea is to get as many number of zeros. So that's another way of also, these are some tricks we play with when using determinants. So what we did here, we had this 3, 4, minus 2. So I said, these two are basically multiples, so these two, are multiples of this numbers, and they actually can get me zeros. So when I do that, I said, I'm going to multiply this twice and add it over here. The change is being brought in this column. What happens? I get a bunch of zeros. Now, it's much more easy to apply cofactor expansion here. So we apply the cofactor expansion on C2. And there we get the answer. Now notice, when we're doing a cofactor expansion, why am I putting a negative here? The reason is this negative is coming from, this is minus 1. Remember, this is just a bunch of zeros. This position is the third row and the second column. So this is 3 plus 2. And then you write down that means this is the minor. Remember, this is minor 3, 2. So this one is 3, negative 2, negative 1, 3. You take the third, remove the third row, the second column. You have 3, minus 1, minus 2, and 3. So when you do the math, you get the answer to be negative 21. Let's look at how this determinant helps us in solving problems of inverses. Okay, a square matrix is invertible if and only if determinant, oops, I forgot guys, of A is non-zero. Remember the invertible matrix theorem also, that also is, it becomes a part of that too. So question is this matrix invertible? So the first thing is, oh, there's a lot of bunch of zeros. And okay, I can apply the cofactor expansion by this or this. But then also notice, wow, this matrix has a bunch of zeros. You know, when you see a bunch of zeros, what does that tell? If you have a matrix, remember that one of the properties, if you have a matrix which has a bunch of zeros, automatically the determinant of this matrix is 0. Which simply implies A is not invertible. Okay. Now, let's look at some other properties. I have two square matrices, A and B, of size n, and I have a non-zero scalar. So there are four properties. Determinant of a scalar multiple. So if I multiply C with A, and I take the determinant, then it is, n is the size, so C, when you take the C out, it has raised n times A. Now, determinant of a product is basically determinant of them individually. Determinant of a transpose and the matrix is the same. Determinant of the inverse of this matrix is nothing but 1 over determinant A. Okay. Now, this is important because remember the scalar multiple. I'm going to go back to the first time we talked about properties. And there was this line where you'll see why it is c to the power n. Let's look at back over here. It says if one row is multiplied by k to produce b, then this determinant b is k times determinant a. That means it was only multiplied either to one row or one column. Yeah, let me write that down too, guys. One row or one column. It does not matter. You know, we can go back and forth between determinants and rows and columns. But be very, very careful. You do not apply that to your normal matrices. It's only when you're talking of determinants we can apply that. Now remember, this is only one row. The key point is one row. Now if the scalar multiple which we're talking about over here is multiplied to every element. Okay, I'm going to take a very simple example for here to you guys. Suppose I have this matrix 2, 4, 6, and 8. Now I want to find the determinant of this matrix. Okay, I will just show you here. What is the determinant? It is 16 minus 24. Answer is 8. It's a simple one. But if I apply this, notice I'm going to apply the properties here. Okay, determinant of A. Now 2 is common in this first row. So if I take the 2 out, then what is left over here is 1, 2, 6, and 8. Okay. Now this 2 has been taken out from here. That's what I have done. That's one it says. If you take one common multiple out of one row, that's how the determinant is. Okay. Notice there's common multiple here in the here. So I'm going to take it out of this column 2. And again, it is a 2, by the way. So I'm going to do the work here. So it is what? 2. Okay, let me, keep the color scheme same so you know what I'm doing. So here is 2. Now this 2 I'm taking out from here, guys, from the column number 2. That's where here, this 2 is coming here. So what are we left with? 1, 1, 6, 4. Okay, now so if you want to take a column out, we can take this also. So we can do that if you want. So what is common here is again 2. So, but at this point, I just like to solve by apply the determinant. It is 4 minus 6. So what do we get here? We have 2. Then we have this 2 coming from the second column. And I simply apply the determinant. which is 4 minus 6, and the answer I still get is a negative 8. So that's why we could have seen, oh, this 2 is common throughout the whole. I could have taken the 2 square out and then have written it down. So it doesn't matter, guys. These properties help us a lot. So let's use these properties to find answers here. Okay. Given that the determinant of the matrix is 4 and the size is a 2 by 2, very important. Remember, sizes are very, very important. So what is the determinant of 3 times a? It's a scalar multiplied to every element in the matrix. So when I take that out, 3 will be the raised to the power of this size, which is 2, determinant of a. So what's 3 squared? 9. 9 times 4 is 36. Okay, let's look at this one, a squared. Now what is a squared? From matrix properties, it is a times a. It's a matrix of 2, a product of 2 matrices. So it's the same as a times determinant a. So this is what, 4 times 4? 16. Okay, let's look at this. So we have 5, A transpose A inverse. So first of all, it is 5 squared because A or A transpose, all of them, they have the same sizes. Then what do we have? We apply the properties which were there. Product of this, it's individual products, A inverse. Now remember, A transpose determinant is the same as A. So this is 25 times A. And what is A inverse, guys? So let's look back. So go up, to the previous slide. A transpose A inverse is 1 over A. So what do we write here? Is 1 over determinant A. Clearly, these cancel out. So final answer is simply a 25. Okay, so now let's look at this adjoint of a matrix. Oops, sorry guys. Okay, now adjoint of a matrix is nothing but related to cofactors of the entries of every element. So let's start with that. First, if I have a matrix, Aij is an n by n matrix, and Cij is a cofactor of Aij. Now, remember, I've been using capital or this, so it's the same thing as, Cij, just to make my life simple, I just wrote it like that. So it is now, we create a matrix of cofactors of A. So what is the adjoint of a matrix? Adjoint of the matrix is the transpose of the matrix of cofactors of A. It is denoted by adjoint of A. Now this gives us another opportunity to find the inverse of a matrix using determinants and cofactors. So what you normally do is you find the cofactors of every term in the original matrix A, write them down, and then what you do is you take the transpose of this matrix of cofactors, and it gives you the adjoint of A. And to find A inverse, you just need to know the determinant, and you just need to multiply it with the transpose of the matrix of cofactors of A, which is called the adjoint of this matrix. Let's do an example. Now consider this matrix. This is the matrix I have been doing it. So these were the cofactors for each one of them. So the first thing we do is we find the matrix of cofactors. So this one is C11, C12, C13. We write down the matrix. And remember, what is adjoint of A? You transpose this matrix. Remember, the diagonal elements remain the same, and the non-diagonal elements, they flip. So 9 and 3, minus 9 and 3 flip, minus 12, minus 1 flip, 1 and 6 flip. So this is what we have. So if the question is find the inverse of this matrix, what is it? You find the determinant, which we have already done previously, and multiply it to B transpose. So the determinant, as I said, we know is 25 from our previous slides. and the adjoint of A is B transpose, basically which we got from the previous slide, 14, -9, -12, and all these numbers. So then we apply the theorem, guys. When we apply the theorem, which was given earlier, we get A inverse to be 1 over determinant of A, adjoint of A. Just plug and chug and you have your answers. Thank you, guys.